This is the Linear Algebra Lectures video series. You can find more information about this video as well as a link to the written textbook in the description below. Stick around to the end of the video to learn more about this video series and the associated teaching and learning tools I've created for it. Lecture 42, the singular value decomposition. Our objective for this lecture is to compute the singular value decomposition of a matrix. So let's recall that a square matrix A is diagonalizable if A can be written as P D P inverse for some invertible matrix P and some diagonal matrix D. We've seen that not every square matrix is diagonalizable. Our goal for this lecture is to learn how to decompose any m by n matrix, doesn't have to be a square matrix, to create a decomposition QD P inverse. And the key idea here is that for any matrix A, the matrix A transpose times A is symmetric and therefore orthogonally diagonalizable. You can see here that when we take the transpose of A transpose A, we just get A transpose A again. So let's let V1 through Vn be an orthonormal basis for Rn consisting of eigenvectors of A transpose A, and let lambda 1 through lambda n be the corresponding eigenvalues. We want to try to use this information about A transpose A to connect back to the original matrix A. Well, if we take the length of AVI squared, that's AVI dotted with AVI, and by the definition of inner product, that's AVI transpose times AVI. By properties of transpose, that reverses the order of the multiplication, so we get VI transpose AVI. VI is an eigenvector for A transpose A, so A transpose A times VI is just lambda I times VI. Then we can pull the lambda I out and rewrite this as lambda I times VI dot VI. And that's just lambda I because remember the VI's are unit vectors because the V's form an orthonormal basis. So we've shown that the length of AVI squared is lambda I. And so this leads to a definition of what we call singular values of A. So if A is any m by n matrix, we let lambda I be the not necessarily distinct eigenvalues of the n by n matrix A transpose A, and then we define the singular values of A to be sigma I, which is equal to the square root of lambda I. Another way to define this is to just let sigma I be the length of AVI. Now this is an important theorem that's going to lead us into the singular value decomposition. This theorem says that if script B, which is the set containing V1 through Vn, is an orthonormal basis for Rn consisting of the eigenvectors of A transpose A, and we're going to number these so that the eigenvalues are in decreasing order. So lambda 1 is greater than or equal to lambda 2, and so on. And what this means is that if there are any zeros on this list, they're at the end of this list. Remember that all the lambdas are non-negative real numbers, so there might not be any zero eigenvalues here, but if they are, we've ordered this list so that they're at the end. So we suppose that A has R non-zero singular values, which is equivalent to saying that lambda 1 through lambda R are non-zero, and the rest of the list, whatever might be past the subscript R, those are all zeros. And so the theorem says that the vectors AV1, AV2, and so on up through AVR, those vectors form an orthogonal basis for the column space of A. So to prove this theorem, there's several things that we need to establish. So we need to show that this set is an orthogonal basis for the column space of A. Basis means that these vectors span the column space of A and are linearly independent, and orthogonal means that their pairwise dot products are equal to 0. So let's first prove that these vectors span the column space of A. So let's let y be a vector in the column space of A, and our goal is to show that y is a linear combination of these AVI vectors. Well, since y is in the column space of A, y is a linear combination of the columns of A, which means that y can be written as AX for some vector x in Rn. And since script B, which is the set containing all the v's, since that's a basis for Rn, we can write Ci for the coordinates of the vector x in that basis B, and that just means that x is a linear combination of the v vectors with the c's as the weights. And remember that these v's are all eigenvectors for A transpose A. The vectors vr plus 1 through vn all correspond to the eigenvalue 0, but the length of AVI squared, that's lambda I, and that must be 0 if I is between r and n, not including r, but including n. All right, so y is A times x, which is A times that linear combination that we talked about using the coordinates of x in the basis B. We distribute the multiplication of our A. We've established that the vectors AVR plus 1 through AVN are all the 0 vector. And that lets us write y as a linear combination of AV1 through AVR, which shows that y is in the span of those vectors, which is what we were trying to prove in this step. Now going the other way, every vector in the set AV1 through AVR is a linear combination of the columns of A because they all look like A times a vector. And that means that every vector that is a linear combination of those vectors must also be in the column space of A. So that shows that the set AV1 through AVR is a spanning set for call A. Next, we have to show that the set containing the vectors AV1 through AVR is an orthogonal set. So remember that the set script B, which contains all the V vectors, is an orthonormal basis for Rn. And to show that the set AV1 through AVR is orthogonal, we let I and j be different subscripts and look at AVI.AVJ. Our definition of inner product says that we can rewrite that as AVI transpose times AVJ. Properties of transpose means that this gets rewritten as VI transpose A VJ. And remember that Vj is an eigenvector for A transpose A, so that turns into lambda j Vj. We can pull out the lambda j, and we get Vi.Vj. But script B was an orthonormal basis, which means that the V's are orthogonal to each other. So that means that Vi.Vj is 0, and then lambda j times 0 is 0. So that shows that this set is orthogonal. And then finally, we proved in lecture 38 that any orthogonal set of non-zero vectors is linearly independent. And this set, AV1 through AVR, contains only non-zero vectors because we ordered our list so that all of the zero vectors were at the end. And so we've eliminated the vectors AVR plus 1 through AVN. Those were the zero vectors in this set. We cut those vectors out, and so that means that this is an orthogonal set of non-zero vectors and therefore linearly independent. Now, to get started with the singular value decomposition, we need to define a not quite diagonal matrix. Remember that A itself is not necessarily a square matrix. And so the decomposition that we're going to see involves a matrix that has the same shape as A. This matrix sigma is m by n, and it's mostly zeros. The only non-zero entries of sigma are the diagonal entries in row I, column I, and the row I, column I entry is sigma I, where sigma is the corresponding singular value. So here's the decomposition, and here's what the theorem says. If A is an m by n matrix with r non-zero singular values, sigma 1 through sigma r, then A can be written as U sigma V transpose, where U is an m by m matrix. Sigma is the m by n almost diagonal matrix that we were just looking at on the previous slide, and V is an n by n orthogonal matrix. Remember, no matter what matrix A we start with, the square symmetric matrix A transpose A is orthogonally diagonalizable by the symmetric matrix theorem. So just like we did in the previous theorem, we'll define script B to be V1 through Vn, and that's going to be an orthonormal basis for Rn, consisting of eigenvectors of A transpose A, corresponding to eigenvalues lambda I that are written in decreasing order. And we proved earlier that the set containing AV1 through AVR is an orthogonal basis for the column space of A. Now, since A has m rows, call A is a subspace of Rm, and so what we're going to do is normalize each of the vectors AVI to obtain an orthonormal basis, U1 through UR, for this subspace, call A. So UI is 1 divided by the length of AVI times AVI. But remember that the length of AVI is just sigma I. So the vector UI is 1 over sigma I times AVI. Or we can multiply both sides by sigma I to rewrite this as AVI is sigma I UI. So remember that equation for later. AVI equals sigma I UI. That's going to be important here in a minute. Now, if R is less than m, we want to extend this set of U vectors to a full orthonormal basis for all of Rm. And we learned how to do this in lecture 40, and we've done it a few times since. We form the matrix C that has those vectors as its columns, and since the orthogonal complement of the column space of C is the null space of C transpose, we find an orthonormal basis for null C transpose. We row reduce C transpose, write the solution in parametric vector form, and we apply Gram-Schmidt to those solution vectors if necessary. So once we do that, we'll have a full orthonormal basis for Rm. So we let U be the matrix that has those vectors as its columns. So that's a square orthogonal m by m matrix. And we let V be the matrix whose columns are the Vi. So just to help you keep track of what's going on, the columns of U were the normalized basis of the column space of A, extended to a full basis of Rm. And then the V's were the orthonormal eigenvectors of A transpose A. And it turns out that AV is equal to U sigma, and that'll prove that A is equal to U sigma V transpose, because V is an orthogonal matrix, and so V transpose is equal to V inverse. And again, we're going to use the fact that AVI is equal to sigma I times UI. Okay, so what's AV? The definition of matrix multiplication tells us that when we multiply a matrix times another matrix, we multiply that matrix by the individual columns of the second matrix. So the columns of AV are A times VI. Remember that AVR plus 1 through AVN, those are all the zero vector. And then we also know that AVI is equal to sigma I UI. And so this is what AV looks like. But U sigma, if we multiply U by this not quite diagonal matrix on the right, that's going to have the same effect of multiplying the columns of U by the diagonal entries of sigma. And so these are the same expression. So that proves that AV is equal to U sigma, which proves the theorem. So here's the process for actually computing the singular value decomposition of a matrix. We find an orthogonal diagonalization of A transpose A. To do that, follow the process that we laid out in lecture 41. Then we construct V and sigma. The columns of V are the orthonormal basis of eigenvectors that we found in step 1. And sigma has the same shape as A, and its row I, column I entry is sigma I, which is the square root of lambda I. And then finally, we construct the matrix U. We start out by computing UI is equal to 1 over sigma I times AVI. We do that for all of our non-zero singular values. If that gives us a full M by M matrix, then we're done. But if not, then we'll extend this to a full basis for our M using the process that we talked about. Okay, let's work through an example. So here's a matrix A. We want to construct its singular value decomposition. We'll use technology to help us out. We'll start out by typing the matrix A into Wolfram. We'll compute A transpose A, and then we'll use the eigensystem command to find the eigenvector basis for R3 in this case. So we see that we have 3 eigenvalues of A transpose A. Lambda 1 is 4, lambda 2 is 1, and lambda 3 is 0. And remember that the singular values for A are the square roots of these eigenvalues. So for each of these eigenvalues, we need to find an orthonormal basis for the eigenspace. In this case, we only got one eigenvector for each eigenvalue, so we don't need to worry about orthogonality. Those vectors are automatically orthogonal to each other, as we've proved in a previous lecture. And so all we need to do is normalize those vectors to get an orthonormal eigenvector basis that we need. So we normalize each vector, and that gives us the vectors that we'll call v1 through v3. So those 3 vectors are the columns of V, and the not quite diagonal matrix sigma has the same shape as the original matrix A, which was 4 by 3, and its diagonal entries are the singular values, which again, remember, are the square roots of the eigenvalues that we found. So there's V and there's sigma. All that's left to do is to compute U. So first we compute UI is 1 over sigma I times AVI for each non-zero singular value. We had 2 non-zero singular values. Sigma 1 was 2 and sigma 2 was 1, so that gives us the vectors U1 and U2 here. Now for U3 and U4, we need to extend this basis to a full orthonormal basis for R4. Now C transpose is the matrix that has these vectors as its rows, so we row reduce C transpose to write the solution of C transpose X equals 0 in parametric vector form. So here's our reduced matrix. Our solution is x1 equals negative x2, x2 is free, x3 is free, and x4 is 0. In parametric form, that gives us the vectors negative 1, 1, 0, 0, and 0, 0, 1, 0. And then in Wolfram, we'll use the orthogonalize command to apply Gram-Schmidt to get our vectors U3 and U4. So this matrix has as its columns the 2 vectors that we computed using these singular values. Those are the first 2 columns, U1 and U2, and the third and fourth columns are the vectors that we just found. And we can verify if we type these matrices into Wolfram that U times sigma times V transpose is the original matrix A. Now this is a lot of work, but you can do it all in one step in Wolfram by using the command singular value decomposition. You don't always get the same answer that you'll get by computing it by hand because these decompositions are not unique. Now the singular value decomposition spits out a list of matrices. It gives you the matrix U first, sigma second, and V third. So that's how you interpret the result if you use this command in Wolfram. Now I've got one more lecture in this lecture series, and that's where we're going to see some applications of this singular value decomposition. Thanks for watching this video lecture. You can find links to the other videos in this series and to the written textbook in the description below. If you're an instructor, you can contact me for more information about the over 300 online linear algebra homework problems that I've created for the free My Open Math platform.